Section 9.1.5, Testing with Files on Disk. Consider an operator that reads one file holding a list of JSONs and writes these to CSV format, figure 9.7. The operator for this operation could look as follows. This JSON to CSV operator takes two input arguments, the input JSON path and the output CSV path. To test this operator, we could store a static file in our test directory to use as input for the test. But where do we store the output file? In Python, we have the temp file module for tasks involving temporary storage. It leaves no remainders on your file system since the directory and its contents are wiped after usage. Once again, PyTest provides a convenient access point to this module named tmp_dir, gives os.path object, and tmp_path gives pathlib object. Let's view an example using tmp_path. Upon starting the test, a temporary directory is created. The tmp_path argument actually refers to a function, which is executed for each test it is called in. In PyTest, these are called fixtures. See this link. While fixtures bear some resemblance with unit tests, setup, and teardown methods, they allow for greater flexibility because fixtures can be mixed and matched. For example, one fixture could initialize a temporary directory for all tests in a class, while another fixture only initializes for a single test. The default scope of fixtures is every test function. We can see this by printing the path and running different tests, or even the same test twice. Footnote 7. Look up PyTest scope if you're interested in learning how to share fixtures across tests. This will print, respectively, this and this. There are other fixtures to use, and PyTest fixtures have many features that are not demonstrated in this book. If you're serious about all PyTest features, it helps to go over the documentation. Section 9.2, Working with DAGs and Task Context in Tests. Some operators require more context, for example, templating of variables, or usage of the task instance context for execution. We cannot simply run operator.execute context equals curly brackets like we did in the previous examples because we provide no task context to the operator, which it needs to perform its code. In these cases, we would like to run the operator in a more realistic scenario, as if Airflow were to actually run a task in a live system and thus create a task instance context, template all variables, and so on. Figure 9.8 shows the steps that are performed when a task is executed in Airflow. Footnote 8. In task instance _run_raw_task. As you can see, step 5 is the only one we've run in the examples so far, listings 9.15, 9.17, and 9.20. If running a live Airflow system, many more steps are performed when executing an operator, some of which we need to execute to test, for example, correct templating. Say we implemented an operator that pulls movie ratings between two given dates, which the user can provide via templated variables. This operator is not testable, as in the previous examples, since it potentially requires the task instance context to execute. For example, the output_path argument could be provided as /output/curly brackets ds curly brackets.json, and the ds variable is not available when testing with operator.execute context equals curly brackets. So for this, we'll call the actual method Airflow itself also uses to start a task, which is operator.run, a method on the base operator class. To use it, the operator must be assigned to a DAG, while the previous example could be run as is, without creating a DAG for testing purposes. In order to use run, we need to provide a DAG to the operator, because when Airflow runs a task, it refers to the DAG object on several occasions, for example, when building up the task instance context. We could define a DAG in our tests as follows. The values we provide to the test DAG doesn't matter, but we'll refer to these while asserting the results of the operator. Next, we can define our task and run it. If you run the test as we've defined it now, you will probably encounter an error similar to the following listing. As you can tell from the error message, there's something wrong in the Airflow metastore. To run a task, Airflow queries the database for several pieces of information, such as previous task instances with the same execution date. But if you haven't initialized the Airflow database, Airflow DB init in the path Airflow_home is set to approximately /Airflow if not set, or configured Airflow to a running database, then it will have no database to read or write. So also when testing, we will need a metastore. There are several approaches to deal with the metastore during testing. First, hypothetically, we could mock every single database call, as shown before, when querying for connection credentials. While this is possible, it is very cumbersome. A more practical approach is to run a real metastore that Airflow can query while running the tests. To do this, you run Airflow DB init, which initializes the database. Without any configuration, the database will be a SQLite database, stored in approximately /airflow/airflow.db. If you set the Airflow_home environment variable, Airflow will store the database in that given directory. Ensure that while running tests, you provide the same Airflow_home value so that Airflow can find your metastore. Footnote 9. To ensure your tests run isolated from anything else, a Docker container with an empty initialized Airflow database can be convenient. Now, once you've set up a metastore for Airflow to query, we can run the test and see it succeed. Also, we can now see a row was written to the Airflow metastore during the test. Figure 9.9. Footnote 10. dbeaver is a free SQLite database browser. There are two things to point out in this test. If you have multiple tests using a DAG, there is a neat way to reuse it with PyTest. We've covered PyTest fixtures, and these can be reused over multiple files in subdirectories using a file named conftest.py. This file can hold a fixture for instantiating a DAG. Now, every test requiring a DAG object can simply instantiate it by adding test_DAG as an argument to the test, which executes the test_DAG function at the start of the test. Task.run is a method on the base operator class. Run takes two dates and, given the DAG's schedule_interval, computes instances of the task to run between the two given dates. Since we provide the same two dates, the DAG's starting date, there will be only one single task instance to execute. Section 9.2.1. Working with external systems. Assume we're working with an operator that connects to a database, say a MovieLens to Postgres operator, which reads MovieLens ratings and writes the results to a Postgres database. This is an often seen use case, when a source only provides data as it is at the time of requesting but cannot provide historical data, and people would like to build up history of the source. For example, if you queried the MovieLens API today, where John rated The Avengers with 4 stars yesterday but today changed his rating to 5, the API would only return his 5-star rating. An Airflow job could, once a day, fetch all data and store the daily export together with the time of the writing. The operator for such an operation could look like this. Let's break down the execute method. It connects the MovieLens API and Postgres database by fetching data and transforming the results into queries for Postgres, figure 9.10. How do we test this, assuming we cannot access our production Postgres database from our laptops? Luckily, it's easy to spin a local Postgres database for testing with Docker. Several Python packages exist that provide convenient functions for controlling Docker containers within the scope of PyTest tests. For the following example, we'll use PyTest Docker tools. See this link. This package provides a set of convenient helper functions with which we can create a Docker container for testing. We won't go into all the details of the package, but we'll demonstrate how to create a sample Postgres container for writing MovieLens results. If the operator works correctly, we should have results written to the Postgres database in the container at the end of the test. Testing with Docker containers allows us to use the real methods of hooks without having to mock calls, with the aim of testing as realistic as possible. First, Install pytest docker tools in your environment with pip install pytest_docker_tools. This provides us a few helper functions, such as fetch and container. First, we will fetch the container. The fetch function triggers Docker pull on the machine it's running on, and therefore requires Docker to be installed, and returns the pulled image. Note the fetch function itself is a pytest fixture, which means we cannot call it directly, but must provide it as a parameter to a test. Running this test will print. We can now use this image ID to configure and start a Postgres container. The container function in pytest_docker_tools is also a fixture, so that too can only be called by providing it as an argument to a test. It takes several arguments that configure the container to start, in this case, the image ID, which was returned from the fetch fixture, and the ports to expose. Just like running Docker containers on the command line, we could also configure environment variables, volumes, and more. The ports configuration requires a bit of explanation. You typically map a container port to the same port on the host system, that is, docker run-p5432:5432 Postgres. A container for tests is not meant to be a container running until infinity, and we also don't want to conflict with any other ports in use on the host system. Providing a dict to the port's keyword argument, where keys are container ports and values mapped to the host system, and leaving the values to none, will map the host port to a random open port on the host, just like running docker run-p. Providing the fixture to a test will execute the fixture, that is, run the container, and pytest docker tools then internally maps the assigned ports on the host system to a ports attribute on the fixture itself. This gives us the assigned port number on the host, which we can then use in the test to connect to. In order to mimic a real database as much as possible, we'd like to set a username and password and initialize it with a schema and data to query. We can provide both to the container fixture. Database structure and data can be initialized in postgres-init.sql. In the container fixture, we provide a Postgres username and password via environment variables. This is a feature of the Postgres Docker image. It allows us to configure several settings via environment variables. Read the Postgres Docker image documentation for all environment variables. Another feature of the Docker image is the ability to initialize a container with a startup script by placing a file with extension star.sql, star.sql.gz, or star.sh in the directory /docker-entrypoint-initdb.d. These are executed while booting the container before starting the actual Postgres service, and we can use these to initialize our test container with a table to query. In listing 9.31, we mount a file named postgres-init.sql to the container with the volumes keyword to the container fixture. We provided a dict where the keys show the absolute location on the host system. In this case, we saved a file named postgres-init.sql in the same directory as our test script, so this will give us the absolute path to it. The values are also a dict where the key indicates the mount type, bind, and the value of the location inside the container, which should be in /docker-entrypoint-initdb.d in order to run the star.sql script at boot time of the container. Put all this together in a script and we can finally test against a real Postgres database. The full test turns out a bit lengthy because of the container initialization and the connection mocking we have to do. After this, we instantiate a Postgres hook, which uses the same mocked get_connection as in the movie lens to Postgres operator, and thus connects to the Docker Postgres container. We first assert if the number of rows is 0, run the operator, and finally test if any data was inserted. Outside the test logic itself, what happens? During test startup, pytest figures out which tests use a fixture and will execute only if the given fixture is used, figure 9.11. At the time PyTest decides to start the container fixture, it will fetch, run, and initialize the container. This takes a couple of seconds, so there will be a small delay of a few seconds in the test suite. After the tests finish, the fixtures are terminated. PyTest Docker Tools puts a small wrapper around the Python Docker client, providing a couple of convenient constructs and fixtures to use in tests. Section 9.3. Using tests for development. Tests not only help for verifying the correctness of your code, they are also helpful during development because they allow you to run a small snippet of code without having to use a live system. Let's see how they can help us while developing workflows. We will show a couple of screenshots of PyCharm, but any modern IDE will allow us to set breakpoints and debug. Let's go back to the movie lens popularity operator shown in section 9.1.3. In the execute method, it runs a series of statements, and we would like to know the state halfway through. With PyCharm, we can do this by placing a breakpoint and running a test that hits the line of code the breakpoint is set to, figure 9.12. Now run the test_movie lens popularity operator test and start it in debug mode, figure 9.13. Once the test reaches the line of code on which you've set a breakpoint, you can inspect the current state of variables, but also execute code at that moment. Here we can, for example, inspect the task instance context halfway through the execute method, figure 9.14. Sometimes your code works locally, but returns an error on a production machine. How would we debug on a production machine? There is a way to debug remotely, but that's beyond the scope of this book. It allows you to connect your local PyCharm or other IDE debugger to a remote running Python process. Search for PyCharm Remote Debugging for more information. Another alternative, if for whatever reason you cannot use a real debugger, is to resort to a command line debugger. For this, you need access to the command line on the remote machine. Python has a built-in debugger named PDB, Python Debugger. It works by adding this line of code on the location you want to debug. Footnote 11. With Python 3.7 and PEP 553, a new way to set breakpoints was introduced, simply by calling breakpoint. Now you can start your code from the command line, either by running a test with PyTest or by starting an Airflow task in a DAG with the CLI by running. Here's an example. Airflow tasks test runs the task without registering any records in the metastore. It's useful for running and testing individual tasks in a production setting. Once the PDB breakpoint is reached, you can execute code and control the debugger with certain keys, such as N for executing the statement and going to the next line, and 1 for displaying the surrounding lines, figure 9.15. See the full list of commands by searching for PDB cheat sheet on the internet. Section 9.3.1. Testing complete DAGs. So far, we've focused on various aspects of testing individual operators, testing with and without task instance context, operators using the local file system, and operators using external systems with the help of Docker. But all these focused on testing a single operator. A large and important aspect of the development of workflows is ensuring all building blocks fit together nicely. While one operator might run correctly from a logical point of view, it could, for example, transform data in an unexpected way, which makes the subsequent operator fail. How do we ensure all operators in a DAG work together as expected? Unfortunately, this is not an easy question to answer. Mimicking a real environment is not always possible, for various reasons. For example, with a DTAP, development, test, acceptance, production, separated system, we often cannot create a perfect replica of production in the development environment because of privacy regulations or the size of the data. Say the production environment holds a petabyte of data. Then it would be impractical, to say the least, to keep the data in sync on all 4 environments. Therefore, people have been creating production environments that are as real as possible, which we can use for developing and validating the software. With Airflow, this is no different, and we've seen several approaches to this problem. We briefly described 2 approaches in sections 9.4 and 9.5. Section 9.4. Emulate production environments with Whirl. One approach to recreating a production environment is a project named Whirl. See this link. Its idea is to simulate all components of your production environment in Docker containers and manage all these with Docker Compose. Whirl comes with a CLI utility to easily control these environments. While Docker is a great tool for development, one downside is that not everything is available as a Docker image. For example, there is no Google Cloud Storage available as a Docker image. Section 9.5. Create DTAP environments. Simulating your production environment locally with Docker or working with a tool such as Whirl is not always possible. One reason for that is security. For example, it's sometimes not possible to connect your local Docker setup with an FTP server used in your production DAGs because the FTP server is IP allow listed. One approach that is often more negotiable with a security officer is to set up isolated DTAP environments. 4 fully fledged environments are sometimes cumbersome to set up and manage, so in smaller projects with few people, sometimes just 2, development and production, are used. Each environment can have specific requirements, such as dummy data in the development and test environments. The implementation of such a DTAP street is often very specific to the project and infrastructure, and is not in the scope of this book. In the context of an Airflow project, it is wise to create one dedicated branch in your GitHub repository per environment: development environment, development branch, production environment, production, main, and so on. This way, you can develop locally in branches. Then, first merge into the development branch and run DAGs on the development environment. Once satisfied with the results, you would then merge your changes into the next branch, say main, and run the workflows in the corresponding environment. Summary. A DAG integrity test filters basic errors in your DAGs. Unit testing verifies the correctness of individual operators. PyTest and plugins provide several useful constructs for testing, such as temporary directories and plugins for managing Docker containers during tests. Operators that don't use task instance context can simply run with execute. Operators that do use task instance context must run together with a DAG. For integration testing, you must simulate your production environment as closely as possible. Chapter 10. Running tasks in containers. This chapter covers identifying some challenges involved in managing Airflow deployments, examining how containerized approaches can help simplify Airflow deployments, running containerized tasks in Airflow on Docker, establishing a high-level overview of workflows in developing containerized DAGs. In previous chapters, we implemented several DAGs using different Airflow operators, each specialized to perform a specific type of task. In this chapter, we touch on some of the drawbacks of using many different operators, especially with an eye on creating Airflow DAGs that are easy to build, deploy, and maintain. In light of these issues, we look at how we can use Airflow to run tasks in containers using Docker and Kubernetes, and some of the benefits this containerized approach can bring. Section 10.1. Challenges of many different operators. Operators are arguably one of the strong features of Airflow, as they provide great flexibility to coordinate jobs across many different types of systems. However, creating and managing DAGs with many different operators can be quite challenging due to the complexity involved. To see why, consider the DAG in Figure 10.1, which is based on our recommender use case from Chapter 8. The DAG consists of 3 different tasks: fetching movie recommendations from our movie API, ranking movies based on the fetched recommendations, and pushing these movies to a MySQL database for further use downstream. Note that this relatively simple DAG already uses 3 different operators: an HTTP operator, or some other API operator, for accessing the API, a Python operator for executing the Python recommender function, and a MySQL operator for storing the results. Section 10.1.1. Operator interfaces and implementations. A drawback of using different operators for each of these tasks is that we need to familiarize ourselves with the interfaces and inner workings of each operator to use them effectively. Additionally, if we were to encounter bugs in any of the operators, we would need to spend valuable time and resources on tracking down the underlying issues and fixing them. While these efforts may seem tractable for this small example, imagine maintaining an Airflow deployment with many different DAGs, which together use a multitude of different operators. In such a scenario, working with all these operators may seem a bit more daunting. Footnote 1. This is unfortunately not unheard of, especially for more esoteric and less frequently used Airflow operators. Section 10.1.2. Complex and conflicting dependencies. Another challenge in using many different operators is that each generally requires its own set of dependencies, Python or otherwise. For example, the HTTP operator depends on the Python library requests for doing HTTP requests, while the MySQL operator depends on Python and/or system-level dependencies for talking to MySQL. Similarly, the recommender code being called by the Python operator is likely to have its own slew of dependencies, such as pandas, scikit-learn, etc., if machine learning were involved. Because of the way that Airflow is set up, all of these dependencies need to be installed in the environment that runs the Airflow scheduler, as well as the Airflow workers themselves. When using many different operators, this requires many dependencies to be installed, leading to potential conflicts, Figure 10.2, and a great deal of complexity in setting up and maintaining these environments, not to mention the potential security risks with installing so many different software packages. Conflicts are particularly a problem in Python environments, as Python does not provide any mechanism for installing multiple versions of the same package in the same environment. Footnote 2. Just look at Airflow's setup.py file for an idea of the sheer number of dependencies involved in supporting all of Airflow's operators. Section 10.1.3. Moving toward a generic operator. Because of these challenges in using and maintaining many different operators and their dependencies, some have argued it would be better to focus on using a single generic operator for running Airflow tasks. An upside of this approach is that we only have to be familiar with one kind of operator, which means that our many different Airflow DAGs suddenly become much easier to understand, as they only consist of one type of task. Moreover, if everyone uses the same operator to run their tasks, we are less likely to run into bugs in this heavily used operator. Finally, having only one operator means we only have to worry about one set of Airflow dependencies, those required for this single operator. But where would we find such a generic operator capable of running many different tasks that at the same time doesn't require us to install and manage dependencies for each? That's where containers come in. Section 10.2. Introducing containers. Containers have been touted as one of the major recent developments that allow applications to be easily packed with the required dependencies and to be easily deployed in different environments uniformly. Before going into how we can use containers within Airflow, we'll first give a short introduction to containers to make sure we're all on the same page. If you're already familiar with Docker and the concepts behind containers, feel free to skip ahead to section 10.3. Footnote 3. For a full introduction, we happily refer you to the many books written about container-based virtualization and related technologies, such as Docker, Kubernetes. Section 10.2.1. What are containers? Historically, one of the biggest challenges in developing software applications has been their deployment, that is, ensuring that your application or applications can run correctly and stably on the target machine or machines. This typically involves juggling and accounting for many different factors, including differences between operating systems, variation in installed dependencies and libraries, differing hardware, and so on. One approach to managing this complexity is to use virtualization, in which applications are installed into a virtual machine, VM, that is running on top of the client's operating host operating system, Figure 10.3. Using this type of approach, applications see just the VM's operating system, OS, meaning that we only have to ensure the virtual OS meets the requirements of our application, rather than modifying the host OS. As such, to deploy our application, we can simply install our application with any required dependencies into the virtual OS, which we can then ship to our clients. A drawback of VMs is that they are quite heavy because they require running an entire operating system, the virtual or guest OS, on top of the host operating system. Moreover, every new VM will be running its own guest operating system, meaning that considerable resources are required to run multiple applications in VMs on a single machine. This limitation led to the development of container-based virtualization, which is a much more lightweight approach than VMs, figure 10.3. In contrast to VMs, container-based virtualization approaches use kernel-level functionality in the host operating system to virtualize applications. This means containers can segregate applications and their dependencies in the same fashion as VMs, but without requiring each application to run its own operating system. They can simply leverage this functionality from the host OS. Interaction between containers and the host operating system is often managed by a service called the container engine, which provides an API for managing and running the different application containers and their images. This service often also provides command line tooling that helps users build and interact with their containers. The most well-known container engine is Docker, which has gained a lot of popularity over the years due to its being relatively easy to use and its large community. Section 10.2.2, Running our first Docker container. To explore the life cycle of building and running a container, let's try to build a small container using Docker. This will hopefully give you a feel for working with containers and the involved development workflow. Before getting started, make sure you have Docker installed. You can find instructions for installing Docker Desktop at this link. Once you have Docker installed and running, we can run our first container using the following command in your terminal. Running this command should give you something like the following output. What happened when we ran this command? In short, Docker performed the following steps for us. 1. The Docker client contacted the Docker daemon, the container service running on our local machine. 2. The Docker daemon pulled a Debian Docker image, which contains the base Debian binaries and libraries, from the Docker Hub registry, an online service for storing Docker images. 3. The Docker daemon created a new container using that image. 4. The container executed our command echo hello world inside the container. 5. The Docker daemon streamed the output from the command to the Docker client, showing it on our terminal. This means that we were able to execute our command, echo hello world, inside an Ubuntu container on our local machine, independent of our host operating system. Pretty cool. Similarly, we can run commands in Python using the following command. This effectively runs our Python command inside the Python container. Note that here we specify a tag for the image, 3.8, which in this case makes sure we use a version of the Python image that contains Python 3.8. Section 10.2.3, Creating a Docker image. Although running an existing image is pretty straightforward, what if we want to include our own application in an image so that we can run it using Docker? Let's illustrate the process with a small example. In this example, we have a small script, fetch_weather.py, that fetches weather predictions from the wttr.in API. See this link, and writes the output of this API to an output file. This script has a couple of dependencies, Python and the Python packages clicks and requests, and we want to package the whole thing as a Docker image so that it is easy for end users to run. We can start building a Docker image by creating a Docker file, which is essentially a text-based file that describes to Docker how to build the image. The basic structure of a Docker file is something like this. Each line of the Docker file is essentially an instruction that tells Docker to perform a specific task when building the image. Most Docker files start with a from instruction that tells Docker which base image to use as a starting point. The remaining instructions, copy, add, env, etc., then tell Docker how to add extra layers to the base image that contains your application and its dependencies. To actually build an image using this Docker file, we can use the following docker build command. This effectively tells Docker to build a Docker image using the current directory as a build context. Docker will then look inside this directory for the Docker file and also search for any files included in add copy statements, such as our script and the requirements file. The --tag argument tells Docker which name to assign to the built image. In this case, manning-airflow/wttr-example. Running this build command will give something like the following output. This essentially shows the entire build process involved in creating our image, starting with the Python base image, step 1, up until our final CMD instruction, step 7, finished by Docker, stating it tagged the build image with the provided name. To do a test run of the build image, we can use the following command. This should print the following help message from our script inside the container. Now that we have our container image, we can start using it to fetch weather forecasts from the WTTR API in the next section. Section 10.2.4, Persisting Data Using Volumes. We can run the WTTR-example image we built in the previous section to fetch the weather for a city like Amsterdam using the following Docker command. Assuming everything goes correctly, this should print some weather forecasts for Amsterdam in the terminal, together with some fancy graphs. Figure 10.4. To build some history of weather forecasts, we may also want to write the forecasts to some output file or files that we can use for future reference or analysis. Fortunately, our CLI script includes an extra argument, --output_path, which allows us to specify an output file path to write the forecasts to, instead of writing them to the console. However, if you try to run this command with a local file path, you will see that it doesn't actually create any JSON output on your local file system. This is because your container environment is isolated from your host operating system, which means that it, among other things, has an isolated file system separated from the host file system. To share files with your container, you need to make sure that the files are available in a file system your container has access to. One commonly used option is to read/write files using storage that can be accessed via the internet, such as Amazon's S3 storage or the local network. Alternatively, you can mount files or folders from your host system into the container to make them accessible from within the container. To mount a file or folder into your container, you need to supply a --volume argument to Docker run that specifies the file, folder to mount and the desired path inside the container. This effectively tells Docker to mount the local folder data under the path /data within the container. This means that we can now write our weather output to the mounted data volume using the following command. We can verify everything worked by checking if the text file indeed exists after our container finished running. When you're done with running containers, you can use the following command to check if any containers are still secretly running. You can stop any running containers with Docker's stop command, using the container IDs obtained from the previous command to reference the running containers. Stopped Docker containers still hang around in a suspended state in the background in case you want to start them again at a later point in time. If you don't need the container anymore, you can fully remove the container using Docker's rm command. Note that stopped containers aren't visible by default when using Docker's ps command to look for running containers. You can view stopped containers by including the -a flag when running the ps command. Section 10.3, Containers and Airflow. Now that we have a basic understanding of what Docker containers are and how they can be used, let's turn back to Airflow. In this section, we'll dive into how containers can be used within Airflow and what potential benefits they can bring. Section 10.3.1, Tasks in Containers. Airflow allows you to run your tasks as containers. In practice, this means that you can use container-based operators, such as the Docker operator and the Kubernetes pod operators, to define tasks. These operators will, when executed, start running a container and wait for it to finish running whatever it was supposed to, similar to Docker run. The result of each task depends on the executed command and the software inside the container image. As an example, consider our recommender DAG, figure 10.1. The original example uses 3 operators to perform 3 different tasks, namely fetching ratings using the HTTP operator, ranking movies using the Python operator, and posting the results using a MySQL-based operator. Using a Docker-based approach, figure 10.5, we could replace these different tasks using the Docker operator and use it to execute commands in 3 different Docker containers with the appropriate dependencies. Section 10.3.2. Why use containers? Of course, this kind of container-based approach does require building images for each of the tasks, although sometimes you might be able to share images between related or similar tasks. As such, you might wonder why you would go through the hassle of building and maintaining these Docker images instead of implementing everything in a few scripts or Python functions. Easier dependency management. One of the biggest advantages of using Docker containers is that they provide an easier approach for managing dependencies. By creating different images for different tasks, you can install the exact dependencies required by each of the tasks into their respective image. As tasks then run in isolation within these images, you no longer have to deal with conflicts in dependencies between tasks, figure 10.6. As an additional advantage, you don't have to install any task dependencies in the Airflow worker environment, only in Docker, as the tasks are no longer run directly on the workers. Uniform approach for running different tasks. Another advantage of using containers for tasks is that each containerized task has the same interface, as they're all effectively the same operation, running a container, executed by the same operator, for example, the Docker operator. The only differences are the involved images, with some slight variation in their configuration and executed command. This uniformity makes it easier to develop DAGs, as you only have to learn one operator. And if any operator-related issues pop up, we only have to debug and fix issues in this one operator, instead of having to be intimately familiar with many different ones. Improved testability. Finally, another benefit of using container images is that they can be developed and maintained separately from the Airflow DAG in which they run. This means that each image can have its own development lifecycle and can be subjected to a dedicated test suite, for example, running on mock data, which verifies whether the software in the image does what we expect. The separation into containers makes this testing easier than, for example, using the Python operator, which often involves tasks that are tightly coupled to the DAG itself, thus making it hard to test the functions separate from Airflow's orchestration layer. Section 10.4. Running tasks in Docker. After this introduction, it's time to implement a part of our recommender DAG in containers. In this section, we'll dive into how to run the existing DAG in containers using Docker. Section 10.4.1. Introducing the Docker operator. The easiest way to run a task in a container with Airflow is to use the Docker operator, which is available in the Apache-Airflow-Providers-Docker provider package. As the name of the operator insinuates, the Docker operator allows you to run tasks in containers using Docker. The basic API of the operator looks like this. Footnote 4. For Airflow 1.10.x, you can install the Docker operator using the Apache-Airflow-Backport-Providers-Docker backport package. The idea behind the Docker operator is that it performs the equivalent of a Docker run command, as shown in the previous section, to run a specified container image with specific arguments and wait for the container to finish doing its work. In this case, we're telling Airflow to run the rank_movies.py script inside the manning-airflow/movielens-ranking Docker image, with some extra arguments indicating where the script should read, write its data. Note that we also provide an extra volumes argument that mounts a data directory into the container so that we can provide input data to the container and also keep the results after the task container finishes. What happens when this operator is actually executed? In essence, what happens is illustrated in figure 10.7. First, Airflow tells a worker to execute the task by scheduling it. 1. Next, the Docker operator executes a Docker run command on the worker machine with the appropriate arguments. 2. Then, if needed, the Docker daemon fetches the required Docker image from the registry. 3. Finally, Docker creates a container running the image. 4. And mounts the local volume into the container. 5. As soon as the command finishes, the container is terminated, and the Docker operator retrieves the results in the Airflow worker. Section 10.4.2. Creating container images for tasks. Before we can run tasks using the Docker operator, we need to build any required Docker images for the various tasks. To build an image for any given task, we need to determine exactly which software and corresponding dependencies are required to execute the task. Once this is clear, we can start creating a Docker file, together with any supporting files, and use Docker build to actually create the required image. As an example, let's look